Hi guys, welcome to Learning Electronics Repair and the curse of the DAS18 Amplifier DAS18 thing, yeah. So I did say I'd be back with this one, changed all the ICs, managed now to fix the problem with the 8.75 volts on the audio input, which we should not have had, and we don't have it anymore. It doesn't blow up, it doesn't go bang, the power light comes on, protect light is off, put a signal in, the signal light comes on, but we don't get any sound. Yeah, so we still have no sound coming out of this thing. Last statement I made is, it's Friday. Yeah, I'll have a look after the weekend. So, I had a quick poke around this morning just to save a bit of time, but you haven't missed anything important. I'll just show you how this is connected up. If we look at the data sheet, we'll see we have a resistor from the output here, another one here, feeding to the input. That's the feedback. So this basically is the connection to the speaker here. Okay, has a capacitor on there, no doubt to filter out the high frequency switching, class C amplifier. So that feeds back to here, and the signal comes in here through a capacitor resistor. Okay. I've traced it out now. Ours is just slightly different in as much as the resistor is the other side of the capacitor, but we basically have that. So let's have a look at our circuit on the PCB. Pin 3 is the input. I had to trace it through. It actually goes to here. Okay, the two end of the resistors actually there and there. In fact, connect together, and then this one here comes back to pin 13, so that's the output of the amplifier there. So that's your feedback basically with these. Okay, and then from here, which was pin 3, also goes to this capacitor. It does go somewhere else as well. Other side of the capacitor goes to another resistor, this one. We can just check the value of that one, 3.3k, and the other side of that we have another one, 330k, and this goes to pin 1 on this op amp. So this is effectively the output from the input, so to speak. This is where your signal's coming in. So we should have an audio signal on here, and we should be able to see that. Okay, whereas I mentioned previously, because this effectively is an op amp input, pin 3 is virtual ground. So with virtual ground, basically you will not see a signal here. Now I explained this on the previous video, but I'm actually going to give you a good analogy here that explains it a little bit better, and you'll always understand virtual ground after this. So, op amps 101. Yeah. Here is our op amp. Inverting input, non-inverting input. Okay. With feedback. So this is the output. Negative feedback back to the input. And in our case, the non-inverting input is connected to ground. So the voltage on here will always be 0 volts. Now, the two rules of op amps. Number 1, no current ever flows into or out from the inputs. Okay. Rule number 2, the output of the op amp will always change to a voltage which it can apply back to the input and put the same voltage on the inverting input as the non-inverting. Sounds a bit complicated, doesn't it? But let me show you. Say we have a signal here. Okay. As the signal here goes positive, because it's inverting, the output of the op amp will go negative. As the input goes negative, the output goes positive. Okay. So when you apply a voltage here, could be a DC voltage, as this goes positive here, the op amp will take the output negative. And how much negative will it take it? By what amount? Well, by just enough to put the voltage here back to the same as the voltage there, which is 0. Okay? And the opposite, but the same, applies when this goes negative, the output goes positive. So this end will vary by enough to keep that point at 0. And the amount it needs to vary by depends on the value of these two resistors. So if they were equal, say 10k, 10k, this has to vary by exactly the same amount as that, so the gain effectively is 1. Okay, if this one is, for example, 100k, and this is still 10k, then the output would have to vary by 10 times as much as the input to keep this point here 0. Okay, that's how the op amp basically works. Now, what this means is that if you put your oscilloscope on here, you will see a signal. And if you put your oscilloscope on here, you will also see a signal which is A, inverted, and B, amplified, or for that matter, reduced, attenuated, by exactly the right amount to keep that 0. And if you put your oscilloscope on here, you'll see nothing. This, as far as your oscilloscope is concerned, is ground. But if you measure with your multimeter, take out a multimeter and we measure from here to here, which is ground, it's not shorted to ground, it's not connected to ground, it just behaves as though it is ground, and that's why it's called a virtual ground. Now that might seem really strange, that you can have a waveform here, voltage, you can have a waveform there, voltage, but no waveform on there. You think, well, how can that work? Well, here's where the analogy comes in. And this makes a lot of sense. Watch. We have a seesaw. Do you remember them seesaws? We had them at the playground when we were kids. Yeah, which had little seats on the end of them. And one person would sit on one end and one would sit on the other end. And by pushing your feet against the ground, you could make this go up and down. Okay? And the person on the other end doing the same. If the lengths of the seesaw from the center point, fulcrum, as it's called, are the same, then this person is going up and down by the same amount as that person is going up and down, but in opposite directions. When this one goes up, this one goes down, and vice versa. What happens at the middle? What happens right there at the center? Is it going up and down? No. It's not moving, is it? That point is not going up and down. Yeah, that's like your virtual ground. So now I'm sure it makes perfect sense from the seesaw how this can be changing in voltage. This can be changing in voltage in the opposite direction. And this point can be standing still. Yeah. So there you go. Quick 5 minutes on op amps. Remember those two things. One, that no current ever flows in or out of the inputs on an op amp. And two, that the op amp will change the output voltage in an attempt to make the two input voltages match each other. Okay? What does this mean? It means we can't measure the audio signal there. We can't test our op amp there. Where can we measure it? Here. Okay? Now we know about the seesaw. Yeah, always remember the seesaw. We know we cannot measure or see the audio signal here, even if the op amp is working. In fact, because the op amp is working. If the op amp is not working, yeah, maybe you'll see a signal there. It's like the wrong way round, yeah? So don't let that fool you. We have to look for the signal on the other side of this resistor, which is down here. Okay, which is the output of this chip. If we have a signal here and the chip or the circuit still isn't working, the only problem we can have on this side of it is if that resistor is open circuit, if the capacitor effectively is open circuit. I know these resistors are okay. We should check them. I did check them previously and they are just fine. These large, physically large resistors tend to fail because they're passing a lot of current. And we can see 202, which is 20 and 2 more zeros, 2K, reads fine. This one, 46.4K, so 46400, reads okay, so they're fine. This one, yeah, 3.2, it's a 3.3K, that's close enough. We'd have to test this capacitor, we can't easily test that in circuit. And then if we look at the other side of the amplifier, we have the same, just this chip is mounted the other way round, yeah, and it should be, by the way. So back to continuity, we have a connection to there through the capacitor. This is the other side of the capacitor, okay, to the resistor, and then from the resistor to pin 1, so that's the same. The resistor reads okay, reads okay, reads okay, and from here we know we go back to the chip, we've already tested that. So another thing we should just consider, whatever's wrong with this appears to be a problem on both amplifiers, but because they're bridged we can't say that for certain. So let's have a look now to see if we actually have a signal getting as far as this resistor. We may see the signal the other side because of the capacitor, so we can have a look at that as well, okay? But that side of the capacitor we wouldn't expect to see anything. I'm using my PC with an online signal generator. I've set the signal to 100 Hz because this is a subwoofer amp, and because my sound card doesn't seem to like working as anything much below that. It does some rather strange things. I've connected the scope, we've got the Finersi scope today. So the first thing I want to have a look at is, do I have output on the amplifiers? Okay, so this is one of the outputs. And I have a waveform, it's not well triggered, but I do have it. I seem to have a lot of noise in this signal, but there seems to be some problem with the earthing on my bench. Yeah, but I do have a signal there, okay? Yeah, it doesn't like to auto trigger on it, of course. There, okay, so I have a signal. If you look at the output from the other amplifier, I have no signal, so that is probably why this isn't working. One amp seems to be working okay. The other one isn't. So let me figure out which amp isn't working, then we'll trace the signal back and see if we can see which one it is. I'll just try and look at the signal on the input. So this is the op amp we were talking about, goes to this resistor. It shows a signal there. What about the other one? So this is the other op amp. Yeah, that has a signal as well. It looks the same as the other one basically, so they look basically the same. So the problem appears to be in one of the actual amplifiers further in than that. It's still a little bit difficult to figure out which one goes to here via the relay, but we go from source to drain on these two, okay, and we go to this large resistor here, so we can see that output comes through here. Okay, that's fairly easy to check. And then on the other ones, again from source to drain, yeah, we have a connection there. Okay, drain to source, and that goes to this resistor, 22 ohms. So we know the resistors are good, so we know which output is which on these resistors. So if we just check there, we'll know for sure which channel is working and which one isn't. While I'm just here, and because both of these chips are being changed and they drive these MOSFETs directly, I know I had short circuit ones. You can see where I've actually soldered these ones. Okay. Just a little bit of flux still left on there. Let's just test these and these. I'm going to take them all out again and just check the MOSFETs. I could try to test them in circuit, but I think just removing them is the way to go. So let's see which ones are the problem, okay? If they are the problem. It could be something else, of course. But at least let's eliminate that, yeah? Because it's so easy to get these things mixed up, I'll put a mark on these. So these are the ones on the right hand side, this side of the amplifier, we put a little mark there. And those look like the ones I've actually changed. Okay, so here we are. These are the two with the red ink on them. These are the two I changed. Now if you look, they look basically the same as these as well. The only difference I can really see is in the middle, where that little circle is. It says GP, GS, AD and AB. So those two do look like a pair and these look like a pair, but they also look original. Let's check them. Okay. N channel MOSFET. So the blue is the gate, so green is the drain in the center. 2.09 volts. That's one of those. Here is the other one. So we'll put the green in the center again. Okay. These are from AliExpress, by the way. 209. Again, drain in the center. Look at the other two. So I think these are the original ones. Yeah, they look the same. So I don't think we have a problem with fake MOSFETs this time. While I have the board here, let's just see if we can check this relay. So just trying to see where the connections actually are on the relay. These are not under the relay, so those ones are. I have a load of them down here. Oh, that's these things in front, I think. Okay, so this is where the relay goes. So you would think that from the two speaker terminals, I guess the relay only has to be in one of them, because basically it just breaks the contact between the two. So from this one here goes to there. That is probably the other end of the connection. That goes to there. I'm expecting this won't go to the relay at all. Oh, actually it goes to there. Interesting, okay. Is this relay any good? I mean, it should read open now. You know, while we're this far in, let's just check. I mean, if the relay was faulty, you'd expect to see a signal on both of these resistors, but only on one of the outputs. That's what we seem to have, or neither of the outputs. But as soon as we're here, and the fact I have to put all this together to test it, I think it might be a good time just to unsolder this relay. Let's just have a look. So I'm not quite sure which contact is which here. There's 5 pins. Okay. You would think 2 would be the coil. kind of makes sense. So that leaves like 3 pins. So I can't see how this is a double pole changeover. I can't see down that side of it because of this inductor in the way. I do hear the relay go click, but actually I may well hear the relay on the power supply go click. It might not be this one. It might be the one that's wired across the NTC. Let's see if I can get this out easily. Another reason I've decided to do this now is the fact I've changed both the ICs, which effectively are an amplifier on a chip. Previously I've tested just about everything else. I've changed the various op amps. I seem to have effectively fixed all the other problems. So it could just be something stupid like this, yeah. Relays can fail, so let's see. Let's see if this will come off easily or not. To give it a good chance, I'll warm it up with hot air. We'll try the braid. If that doesn't work, we'll try the vacuum desoldering tool. Okay, we'll warm it first. Okay, the hot air is definitely helping here. Okay, that came off quite easily, so it was worth doing. Probably quicker than me putting all this back together, and then may end up having to take it all apart again, yeah. So we can see we have a common, we have a normally open and normally closed, and the coil. So it does only switch one contact, which is all it we really need to do. We can see it goes this way round. So the common you would think would go to one of our speakers, maybe. No. So normally open or normally closed. So normally open goes to that one. Normally closed doesn't go anywhere. That's what you'd expect. So this one here, I can see it now. This speaker here just goes directly through something here, I think, like an inductor. Yeah, this one also goes through the inductor, and then this one goes through the relay to there. So you'd assume, because we have to assume, that this point, which is one of the speakers, goes to one of the two amplifiers. Doesn't go to there. Oh, to go via that 22 ohm resistor. That doesn't go anywhere. It's interesting. And the other one, which goes to there, we go to the wiper, and that wiper should go to the other one. And doesn't. Well, we know one of these is working. Oh, it goes there. Okay, it goes here. So that's going to the wiper. That's the amplifier on this side. And the other one, you assume that goes to here. Yes. Yeah, so that all makes sense. Let's test this relay. Actually, which side is the relay in? The relay goes to this one. And that's the one that isn't working. Okay, let's have a look. So I have my bench power supply on 12 volts. Let's just connect that across the coil. Do we hear the relay activate? Yes, it does activate. And then we can just go between the wiper and normally open. It's open, of course. Connect our power to the relay, and then do we have a contact? Yes, we do have a contact. So it has a little bit of resistance. Let's see, let's just zero the meter. No, it has basically zero. So Let's see. Let's see. Okay, it's almost, it's really -0.0002. Very close to being zeroed. What does it have? We have the same. So the relay is good. It looks like probably there's going to be a fault in this circuit. So this is what is switching the relay. I suspect very strongly it isn't switching. Could be wrong. You'd have to check on the ends of these resistors really to see whether or not we have a signal. If we do and we don't on the output, it's definitely the relay. But again, while this is all apart, let's have a quick look around this circuit, see if we can spot anything obvious here. Okay. So this looks like an optoisolator. I'd say that is an optoisolator. We need to test that. See if we can make any sense out of these and circuit. Okay. Nothing there. That reads like a diode, this one. That reads like, not like a diode. Go the other way. That reads not like a diode. This could be a diode, but I'm just trying to figure out if all the 3 pins are actually connected to something or not. You assume that must be connected. Yeah, there's a pad there, so it goes somewhere. So not sure what that thing is. Doesn't really read very sensible. Okay. Let's look at these other ones. I have these 1 AM 2 or 1 AM or I have these. These are transistors. Well, they should be looking like a transistor. I think they're NPN actually. Just turn the equipment off so it's a bit quieter, eh guys? Let's have a look. Yeah, junction. Junction, that looks like it should do. Should be open this way. Well, it's fairly high. Not sure. Junction. Junction. Fairly high. These are in parallel. It's going a bit crazy actually. They look like they might be in parallel. No, just the collectors. Oh, that one there, emitter goes to the base of this one, Luke. Yeah. So one's effectively driving the other one. So this one I'm not sure about. What's this resistor? Here looks a bit cracked or something maybe. That's Luke. No, it reads 22k, which is correct. Okay, what else do we have? 0. My multimeter's doing some very strange things, guys. Look, I've got the wires connected to each other. What on earth is this doing? Okay, not a good day. Maybe the battery's a bit low or something. See, this thing's a lot slower. Do you see that? When I short the leads together, look. It's because it's on the auto ranging. Never mind. So that we know is 0. This one should be 56k. Well, you can read lower in circuit, reads 27, okay. This one, 68 ohm. Yeah. This one, 4.7k. Yeah. This one, 4.7k again. No, 47k, sorry, 4702. 47k. Yeah, it looks okay. And then we have, did we check this one? We'll check it now. 22k. This is a 0 ohm. 0. Let's see what these things are. So they look like diodes. Diode range. Okay. Reads like a diode. Reads sort of like a diode. Oh, it's a xenodiode. Yeah, a xenodiode would read about 0.72. I'm happy with that. This one reads like a diode. And then the optoisolator. So I'm assuming this is the input. The LED end should read like 1.0. Doesn't read anything. This comes through a 22k, so I'm not sure that is the input at all. This says, well, plus is the capacitor, I think. No, the plus is by this. 1.0. I think the plus is the capacitor. There's a plus on that one as well. 1.04. It reads that both ways. Well, the only way to test that is going to be to light up the LED, which I can do with the meter, and put the multimeter across the other side in resistance range. Okay. We'll have to guess the polarity. Red, black on here is reading 34k. And then we need to light the LED on the other side. This is where you need an extra hand, really. Let's try. We can just prop that in there. Hopefully have a contact. Let's see. So when we light the LED, it's changing from 34 to 27. It's not changing much on the resistance. Let's put this into diode mode. Okay. Try again. I'm a bit suspect of that optoisolator. Normally it makes a much bigger difference than that. It may be this optoisolator is faulty. Possibly faulty. Here's a datasheet and this explains something. This is an AC input optoisolator or photocoupler. You see the two diodes. These are LEDs, although they don't show the correct symbol. So that's why we see the 1.04 roughly, which is correct for an infrared LED in both directions. I'm not sure I have these. This was a very common failure, I remember back in the day. So effectively the LEDs in here, the infrared LEDs, lose the emission. They go very dim, so it doesn't switch the transistor properly. It's quite possible this being an AC input one. I haven't traced the circuit, but maybe it's subjected to quite a bit of current. Yeah, I don't know, possible. This here, it says actually Q14, so it looks like it should be a transistor. Marked G1, reads rather strangely. In fact, the battery is low on my multimeter. It's telling me the battery is low. Well, it's not a big problem. We'll use this one for now. I'll get a battery. That's a PP3, I think, and that one 9 volt. So, diode mode. Let's look at this transistor again. Yeah, that doesn't look like a junction of any sort in that direction. This one, junction, no. And then in this direction, let's just go both ways around. I expect it not to read. That doesn't look right. It doesn't look like a MOSFET. We don't see a parasitic diode. It looks rather like a transistor, but with the base collector okay and the base emitter no good. That looks very suspicious. I don't think it's a diode because it says Q14 and because it has a connection on this pin. You can see the via there, so it's not going to be, it could be a double diode, but I'm only seeing one of them if it is. So G1L, what are you? Best way to search for something like this is SMD code, then G1, I'll try it with the L afterwards, SOT23, which is the package. Okay. Oh. Well, that's suggesting this MMBT5551L. I would not be surprised if that's actually correct. SOT23 gives us a couple of choices here. NPN transistor, NPN transistor. NPN, yes, again, NPN transistors. So it looks like there should be an NPN transistor. I have an open circuit base emitter. Again, NPN transistor. As to which one, I really don't know, unfortunately. I wouldn't be surprised if it's one of these because these are quite common. What are the ratings of this thing? Well, 180 volts, that's plenty. Yeah, 0.6 of an amp. I think that'd be a good guess, to be quite honest. I had a look in my stash and I have some of these G1. Assumingly these are the same. These are the MMBT5551. We can test one of these. Let's have a look. So red to the base. Yes, transistor junction. Red to the base emitter. Yeah, transistor junction. So the other one does read faulty. I'm not sure exactly what this is doing in the circuit. This is the coil. So from this end we go to a diode. And the other end of the diode goes back to the coil. So that's the back EMF diode. Okay, so this end would be the positive end of the relay coil. And this would be the negative end because this is reverse biased, of course. So from here, that actually goes to these two in parallel. That's why they're in parallel. And then the other end of those, the two emitters. Well, actually, it looked like one was driving the other here. It is. One is driving the other. That's a bit strange. You would think one of these emitters then goes to ground. Yes, this one does. So that's switching the relay coil to ground. And then the other end of the relay coil will go to the 12 volts. Is that this thing? No, but it must get supply somewhere. We need to see where that supply comes from because I think this relay is not switching. So this other transistor which looks to be faulty. I'm just trying to figure out what this is doing. So this is the emitter. Doesn't go to ground. Oh yes, it does go to ground. That does go to ground. So this here, by the way, is not ground. This thing here, okay? This is like an isolated supply of some sort. So that emitter goes to ground. The collector goes to a resistor here. Where else does it go? Well, that goes to the positive end of the relay coil. That doesn't make a lot of sense because that appears to be wired directly between this point, positive end of the coil, and ground. No, that doesn't go to there. I think what I was trying to do is draw this bit of the circuit out and see if I can figure out what's connected to where. I've reverse engineered this chunk of the circuit. It may not be exactly right, but this is what I'm seeing, and it doesn't totally make sense. So the two transistors Q12 and Q13, this is the one where I could see the collectors were in parallel, but the emitter of one goes to the base of another. Once you draw it out, it's obvious this is a Darlington pair made of two transistors, which just effectively gives the gain, whatever this gain is times whatever that gain is, so it gives more gain. We have 15 volts plus through this resistor, or 77. The resistors all measure okay, by the way. Through the relay we know is working. So if these transistors are switched on, the relay closes. So the contact going to the speaker is normally open. This is the output of amplifier 1, we'll call it. When the relay contact closes, that connects to this end of the speaker. The other end of the speaker just always connected the output of amp 2. Because this is a bridge, it's not an amplifier that can be used either bridge or individually. This is from a active subwoofer, so it's always in bridge mode. So just breaking the contact on either side of the speaker will give you the protection, okay? It doesn't have to have one both sides. That makes sense. So these transistors have to be switched on to close that contact. And we're not seeing any output here, so it looks like that isn't closed. This is a Zener diode. It comes down. This is the transistor that has the open circuit base emitter junction, okay? If you look here, plus 15 volts through the two resistors. There's a capacitor here. The resistors, again, test okay. I didn't test the capacitor. I'm not totally sure what this diode does. This one is to prevent excessive back EMF when the relay switches off, okay? Not totally sure about that. It looks like it, in a way, it's connected in the same polarity at least, but we won't worry about it too much. Normally that shouldn't be conducting, so we go through 56k, 100 ohms to this transistor, and that should put enough voltage on here to turn this on, assuming that the voltage here is greater than the Zener voltage, okay? If the voltage here is less than the Zener voltage, this will turn off, this will turn off, the relay will open. How should that happen? Well, we have this transistor, so 15 volts to the Optoisolator. This is the one with AC input, two LEDs back to back through a 22k to the base. So if the LEDs are lit, or at least one of them is lit, this turns on, turning this transistor on, which pulls this end of the Zener diode to ground, basically. This will now switch off, this will switch off, the relay will open. So we can see that having the LEDs lit means that the relay is open. And when the LED is out, the relay is closed. The problem is that I see an open circuit here. If that is the case, and it is the case, then that effectively doesn't exist. So there should be enough voltage on here to switch this on all of the time, so the relay is closed all the time, regardless of what this is doing. And that is not the fault condition we appear to have. But I do know that transistor's faulty, so I'm going to replace it. I'll leave this for now. I don't have one anyway. It may be okay. We'll put the whole thing back together. We can now check that we have an output on both amplifiers just to be 100% sure this isn't a red herring. And if we do have output on both sides of the amplifier, but we don't have anything here, and we know this is the one that isn't working, this connection, connectors to the speakers are here and here, then we can trace through this to find out why the relay isn't switching on, okay? So that's what we're going to do. I've refitted the relay. I've put the replacement transistor in. We can just check this. Base collector looks good. Base emitter now looks good. I'll fit this back onto the heatsink, then let's put it all back together. Another thing I see with this circuit, this acts like a soft start. So this capacitor has to charge up to a sufficient voltage to get above the Zener voltage before it can turn this transistor on and close the relay contact. And because we have a fairly large value resistor here, 56k, I didn't check the value of the capacitor. It's 47 microfarad, 16 volt from what I see. So it will take some time for that to charge up and for this to turn on. Now, we know this transistor's faulty, and when I say it's open circuit base emitter, it has a bit of a strange reading. So it is possible this is acting as a fairly low resistance from collector to emitter in circuit. And if that is the case, then this capacitor may never charge, or rather this resistor plus whatever resistance this has creates a voltage divider to here. So between one of the two factors, this Zener never gets enough voltage to turn on. So although I say this is open circuit, it's not exactly open circuit, it just doesn't show a diode junction from here to here. So that's another good reason, actually, and that does explain how that transistor being faulty can stop this ever switching on. I've put this back together again. I have it connected to my current limiter. I haven't connected the input yet from the PC, but everything else is connected. The speaker is connected. So let's see what it does now. Well, the same sort of thing on the bulb, so we'll switch that out. I heard two relays click then, did you? Let's connect an input. Bear in mind this is a sub amp, so I'll only hear the bass frequencies. I've plugged an audio signal in, the mix is turned down at the moment. What happens? Oh! That's the first time I've heard that thing work. Okay guys, so it is fixed, yeah. Why did that one take me quite a while? Well, multiple failures basically. So, short circuit MOSFETs on the amplifier. Then the problem with the power supply. When I did find the fault, it blew back up again. So, we had fake MOSFETs causing the second failure on that one. That then took some time to figure out because I had to reverse engineer everything. Then we had the problem on the amplifier again, where we had effectively the all-in-one Class D amp chips blown, or at least one of them was. In fact, both of them, I saw no output on either on that video, and the problem with the op amp with a crack in it and so forth. So we had all that, and then it still didn't work. And at this point, I had to start thinking about this. I'll be quite honest, the actual failure makes perfect sense. I thought only one of the Class D amplifiers were working after I changed those chips. In fact, they were both working, but at this point I found the actual fault. It didn't really occur to me that that would be the nature of the fault on this. So I've learned something here. I'm not going to get fooled by that again, at least not so easily. The fact I could hear a relay going click and the protect light is off just made me assume, therefore, that the speaker was attached. But the relay I could hear was this one. So this actually is connected directly across the NTC, which is here. This prevents a high amount of inrush current when you power up. And in fact, when that went click, if you saw the light bulb, it kind of like goes bright to dim, then it comes back on a little bit bright again and dim. And I assumed again from the way the light bulb was behaving, it was the main amplifier connecting to the speaker. But no, it was this thing. This is what I could hear go click. Okay. I thought it was that one I heard going click. I never even gave it a thought it was the other one. So that's another reason why this kind of threw me a curved bull, shall we say. So, guys, talk about it. Yeah, I'm going to say yay, because I actually fixed this one and I saw this as a challenge. This went way beyond what was economical to repair for the time. It just became something I was determined to fix, and I've done it. Yeah, one tiny, silly little transistor. And the best thing I think we can take away from this, not only did I fix it, I actually figured out what that transistor does and why it didn't work. Okay, chat with me down there. I look forward to seeing you all soon again on Learning Electronics Repair. Ciao for now, guys.